Before we can move on to Newton's second law of motion, we first have to develop a vocabulary for what motion is. We will do that this chapter using position, velocity, acceleration, and time, and exploring how all these variables relate to each other. I am going to use quite a different tact when it comes to exploring these than the book does. That is because I tried going according to the book and I tried only explaining things using math, algebra, and word problems. And when I was editing the finished lecture, I just realized that was complete gobbledygook. Instead, I am going to go into graphical analysis, find the calculus definition of a derivative, and go from there. So, calculus might scare you, but it was developed by Newton especially to explain these laws of motion, and you would have been using it anyways. There are definitions in this book which are just definitions of derivatives that aren't called derivatives. So you would have been using it anyway, and I am just trying to make it so that you can understand what is going on and have a formal understanding of it, even though it might seem scary at first. Before we get down into the big scary calculus, I want to first define position and distance traveled versus speed and velocity because speed is the change in distance over time. It's the rate of change of distance over time, and calculus is the study of rates of change. So I first want to come up with a concrete example before flooring you with graphs and notation and algebraic notation. So to start with, position is a vector quantity which tells you where something is usually given by the variable x for one dimension or r for multiple dimensions. For example, we can say that Menifee is about 25 miles south-southeast of Riverside if we treat Riverside as our origin. Displacement is also a vector quantity, sometimes written as d, big D, which tells the straight line distance and direction between two positions. The displacement between Walnut, which has a position of 32.5 miles north-northwest of Riverside, and Menifee is 57.5 miles south-southeast. And then these are contrasted with the distance travel, which is sometimes called little d, which tells us the absolute amount of distance traveled over the course of an action. So when I drive to and from Menifee, starting from my home in Riverside, the displacement from my start to end point is 0. I start where I end up in my driveway, but the distance traveled is 50 miles. All of these are measured with units of length, meters, feet, kilometers, miles, etc. But displacement and position are vectors, whereas distance traveled is a scalar. And just to be clear, just to give you an idea of what a meter is, it's about 3.2 feet. So they have, what then is the rate of change of distance over time? So v is the variable we use for speed, which is defined as distance divided by time. It has units of length divided by time, so it can be measured in meters per second, kilometers per hour, or miles per hour. But this distance traveled over time is just the average speed. For example, it doesn't tell you how fast you're going at any given instance. You could be going 80 miles per hour on the freeway and 5 miles per hour in the parking lot, and the time that it takes you to get from one place to another the average speed is going to be how much distance you covered overall divided by how much time you covered overall. This is written as v average, the average speed, is equal to delta d over delta t, where delta means the change in something, and delta d over delta t is the change in distance over the change in time, or the distance divided by a time interval. So instantaneous speed is the speed you are going at any given moment and is written, as we are going to discuss in the next slide, as v instantaneous equals dd dt, where we were talking about how you had different speeds at different times. So you were going 80 miles per hour or 5 miles per hour or 20 miles per hour, depending on the different times that you were looking at. Instantaneous speed is therefore the speed that you're going to read on your speedometer and is the speed at any given moment. It is also defined as how much distance is traveled over a time interval as the time interval goes to zero, as the time interval goes infinitely small, or infinitesimally small, rather. So practically, you can't measure an infinitesimally small time period. Therefore, you can't measure an instantaneous speed. If we have these definitions of average speed and instantaneous speed, why do we care about calculus and why do we care about graphs? Well, for one thing, calculus is the study of rates of change. So by looking at speed, which is the rate of change of distance over time, we're already talking about calculus. We just haven't been calling it calculus because that's a scary word. The other is that by looking at graphs, we can tell a lot about the rate of change. And from the rate of change, we can tell about the speed of an object. So, for example, the rate of change can be seen as the slope of a graph. For those of you who don't know, the slope of a graph is given by the rise, or how much the variable on the y-axis rises, how tall it is between 2 points, over the run, how wide it is between 2 points. So for example, in this position versus time graph, the slope of a line between these two blue points would be delta d over delta t. That is also known as V average. So the slope of the line between the 2 points is the slope of the gray line in here, and that it gives you V average. So for a higher slope, delta D would be bigger over the same amount of time, so it would be faster. It would cover more ground in the same amount of time. For a smaller slope, delta D would be smaller for the same amount of time. Therefore, the average would be smaller. So a steep line means that something's going very fast, and a shallow line means that it's going very slow. If we've decided that the slope of the gray line between these two blue points is the average speed between these 2 points, how do we find the instantaneous speed at any of the points? Well, the way that we do that is by taking the definition that we found in the previous slide, where v instantaneous was the change in distance over the change in time as time goes smaller and smaller and smaller and approaches zero, which means that it becomes infinitesimally small, to use the jargon that mathematicians are fond of. So, as this is the case, eventually it's going to come out to a line that just barely touches, which is shown as the red line in this case. This line that barely touches the curve is called the tangent line, and the slope of the tangent line is called the derivative, which is what we found in the previous slide without defining it. By looking at the slopes of these tangent lines at different times, we are able to find the instantaneous velocity at any given time. So instead of just relying on this kind of haphazard gray line that gives us the average velocity, by drawing lines which are tangent to the curve, which means that they are just barely touching, like this, or like this, or like this, we are able to find velocity, or speed rather, as a function of time based on this distance versus time graph. That being said, I kept saying velocity when I meant speed, but you know that from last lecture that velocity is the vector version of speed containing both magnitude and direction. The magnitude of velocity is the speed at which an object is moving, and velocity is given as the derivative of x, the position vector, over time, or just the change in x over the change in time. At this point, we have a pretty good understanding of rates of change of velocity and speed versus distance and position. But how do we solve for distance if all we know is that speed is equal to the distance traveled over time? Well, to do this, we have to do algebra. If you'll remember algebra, what you want to do is take whatever is on the side of the equal sign of the variable that you want to isolate and do the opposite type of operator in order to get rid of all the other variables on its side of the equal sign. And if you do this, you have to do the same thing on both sides of the equal sign, otherwise it's not going to be true anymore. So if we have V average equals D over T, we want to get rid of the T and isolate D. So we multiply both sides by T, which is going to give us T times V average is equal to D times T over T, which is equal to D times 1, which is equal to D. Or the distance traveled is equal to V average times T. This also generalizes to the vector form where the position minus the initial position is equal to the velocity average times t. For our final definition of motion and rates of change, we are going to define acceleration. If a velocity is the rate of change of position over time, acceleration is the rate of change of velocity over time. It has units of velocity divided by time, which is units of length divided by time, which is going to give you length divided by time squared. So the SI units of acceleration are going to be meters per second squared, or you can also have kilometers per hour squared, or miles per hour, or any number of other equation or of other units, but meters per second squared are what we are going to be using mostly for this class. So acceleration is equal to the change in velocity over the time interval, otherwise known as acceleration is equal to the derivative of velocity over time. With these three concepts, we can start looking at position, velocity, and acceleration versus time graphs and understanding how these rates of change relate to each other and how they describe the motion of an object. So for a stationary object, x, the position, is going to be at the same point for the entire time. It's not going to go up and down. This means that its slope is 0. It's a straight horizontal line. It will never have a rise, therefore it will never have a slope, and the velocity is therefore constantly 0. Acceleration is also 0 because as with the velocity graph, the velocity is never going to change, therefore the acceleration never changes. With constant velocity in the second row, we see that velocity is no longer 0, but it is a constant value, which means that there is no acceleration. But as we established a couple slides ago, if you have distance versus a constant velocity, then the distance is going to be equal to the velocity times time, or a linear function. This also makes sense graphically and talking about what we were talking about earlier, where the slope of a line is going to be constant. Therefore, its velocity is constant because the slope of the position versus time graph is equal to the velocity at any given time. For the last row, we have motion with constant acceleration, which is when acceleration is just a constant line, it's a constant horizontal line. But what this means is that since acceleration is the rate of change of velocity, the velocity graph is going to increase linearly like we were seeing with the position versus time graph when velocity was constant. Because it increases linearly, the slope of the position versus time graph is going to get taller and taller and taller as velocity increases, which means that it's going to cover more and more ground the longer time goes on. This is cheating a little bit, but this equation that it's going to follow is, instead of being linear or a straight horizontal line, is going to be a quadratic equation where x is going to be proportional to t squared. This gives us the kinematics equations for constant acceleration, where kinematics is the study of motion. Position is given by the initial position, which is what x naught means, plus the initial velocity times t, plus 1/2 the acceleration times t squared. And velocity is given as we saw in that previous graph, and using the same algebra that we use for constant velocity, the position versus time for a constant velocity. Velocity is given by the initial velocity plus the acceleration times time. With linear motion, basically the only difference that you can find in a vector is whether it has a positive or a negative value. So the sign conventions for linear motion are that linear motion is in one dimension, meaning that you are going forwards or backwards in the straight line. So from the origin, Riverside in my earlier example, designate one direction to be positive towards Walnut and one direction to be negative towards Menifee. A negative velocity means the object is moving towards the negative direction, while a positive velocity means the opposite. This does not mean that the object has a positive or negative position. For example, I could be driving north to Riverside from Menifee for a positive velocity, but I would still be south of my origin, which is Riverside, which means I would have a negative position. And then a negative acceleration means that velocity is becoming more negative, but does not necessarily say anything about positive or negative signs of velocity or position. Everything I've said so far in this lecture has not actually been physics. It's just been mathematics. It's true if you have any sort of motion and rates of change or time. If any of those exist, then everything that I said is going to be true. What is going to be physics is this thought experiment by Galileo, or not even a thought experiment, a real experiment, where he took balls of various materials and various weights and rolled them down slopes. And what he found was that for each slope, the balls would accelerate at a constant acceleration that got higher and higher the steeper the slope was. So it didn't matter if you had a wood ball or an iron ball, it would still accelerate at the same acceleration up until you reach the point where the slope was completely vertical, and then it would be at its maximum value, which is what we call free fall. So Galileo found that every object, no matter how heavy, would fall accelerating at a rate of about 9.81 meters per second squared towards the Earth. In this class, we'll round this to 10 meters per second squared to make calculations easier. So with no initial velocity, we can use our kinematics equations and say that the speed of an object in free fall is given by v equals gt, where g is the 10 meters per second squared and is just substituted into acceleration because it is a constant on the surface of the Earth. And then with no initial velocity, the distance an object falls in free fall is given by d equals 1/2 gt squared. Again, that's just our kinematics equation with no initial velocity and no initial position. Using a pretty standard experimental setup with a motion detector which detects the height of a ball as it bounces up and down and its velocity as it bounces up and down, you can actually prove that this value of g is what Galileo said it was and that it is constant. For example, looking at these graphs, you can see that the position versus time graph is parabolic, which is what we expect from a constant acceleration. But more tellingly, the velocity versus time graph is a straight line, which is definitely what we expect if there's a constant change in velocity over time. Looking at the line of best fit for this velocity versus time graph, we see that the line has a slope of negative 9.776 meters per second squared, which is pretty close to the accepted value of 9.81 meters per second squared. Looking at the position versus time graph versus the velocity versus time graph, we see that up until the line which I drew, the velocity is going to be positive, but it is decreasing in magnitude, which means that the ball is going up, but the slope should be going down, which is what we see with the position versus time graph. Additionally, once you pass that point, the velocity versus time graph is getting steadily stronger negative velocity, which means that the slope should be negative, pointing down and getting steeper, which is also what we see. Finally, at that orange line, you see that the velocity versus time graph is at 0, and the slope of the position versus time graph is also 0 because it is at a turning point where it is stopping going up and is starting to go down. Once the ball hits the floor, it then bounces up and creates another parabola. While this parabola doesn't go to the same height as the first one due to a lack of initial velocity, not all of the velocity was transferred back when it hit the ball. It is still a parabola and it is still in free fall. So as the ball bounces, it is always going to be experiencing a constant negative acceleration of negative 9.776 meters per second squared as the ball bounces, as long as it isn't currently hitting the floor. And now follow some of the examples that are actually in the book. The first is looking at the distance that an object has fallen with no initial velocity versus time. This distance is going to be equal to 1/2 gt squared, which is equal to 1/2 10 meters per second squared times 1 second squared after the first second. This is going to give you 5 meters as your final value for 1 second. For 2 seconds, this is equal to 1/2 times 10 meters per second squared times 2 seconds squared, which is going to give you 5 times 4 is equal to 20 meters. And then d equals 1/2 times 10 times 3 squared is equal to 5 times 9 is equal to 45 meters. So what we see here is, as we saw with our parabolic graph, the distance traveled increases quite a bit over every second that it travels. So from 0 to 1 second, it only travels 5 meters. But from 1 to 2 seconds, it travels a total of 15 meters. And from 2 to 3 seconds, it travels 25 meters. What this means is that it is accelerating. This is the meaning of acceleration. The velocity gets faster the more time passes. Looking at the right-hand side, we see an object that is thrown into the air that actually does have an initial velocity. With this initial velocity, instead of following this simple 1/2 gt squared formula, the velocity actually changes as time goes by. So v of 0 seconds equals 30 meters per second. So that is our v naught. That's our initial velocity. And then minus 10 meters per second squared times t is going to give us our final velocity, or velocity as a function of time. So at 1 second, this is equal to 30 meters per second minus 10 meters per second squared times 1, which is going to be equal to 20 meters per second. And then at 3 seconds, this is going to be equal to 30 minus 10 times 3, which is going to be equal to 0 meters per second. And at t equals 6 seconds, this is going to be equal to 30 minus 10 times 6, which is actually going to be a negative 30 meters per second. So what this means, and what we've seen in our graphs, is that as you throw the ball up, at each time, it is going to be going at a smaller velocity. So it starts out at 30 meters per second. At 1 second, it's 20 meters per second. At 2 seconds, it's at 10 meters per second. And at 3 seconds, it's at standstill, which means that it's turning around and starting to come down and accelerate. So it slows down as it goes up, and it speeds up as it comes down. As much as for an exercise in algebra as anything else, we are going to rearrange the free fall equation to ask how long it takes for an object to fall a certain distance. So the algebra that's involved is going to be a little bit more complicated than what we've seen before. We have the equation d equals 1/2 gt squared. In order to get t squared isolated, we have to divide by 1/2 gt, or 1/2 g on both sides. So d divided by 1/2 g equals t squared, or 2d over g is equal to t squared. Now, this part we haven't been over before, which is the fact that instead of just being by itself, t is squared in this case. So in order to isolate t, we have to take the square root of both sides because the square root of t squared is equal to t. So the square root of t squared is equal to square root of 2d over g, or t is equal to the square root of 2d over g. This is technically not complete as it should be plus or minus square root of 2d over g. However, we can kind of just assume that because you're following from time equals 0, that the time that you fall down is going to be positive because that is generally how time works. So with a value of d equals 1.25 meters, which is about chest height, t is going to be equal to 2 times 1.25 meters divided by 10 meters per second squared, which is equal to the square root of 2.5 meters times second squared divided by 10 meters. Cancel these out. This is going to be equal to 0.25 seconds squared, or 0.5 seconds, because you're taking the square root of 0.25 and the square root of second squared, which is just going to give you 0.5 seconds, which seems like a pretty reasonable amount of time for something to fall from about chest height. In overview, we talked about rates of change and position and time for these three types of vectors: position, velocity, and acceleration. So the position vector just tells you where something is. So San Francisco is a position, Livermore is also a position. Velocity tells you the rate of change of position over time. So if you leave San Francisco moving at 300 kilometers per hour east, then that gives you a magnitude of the rate of change and a direction of the rate of change, which makes it a velocity. And then the acceleration is the rate of change in velocity due to either a change in speed and or a change in direction. So for the first example, we have a change in speed of but not direction, which is a car accelerating and decelerating along a straight road. For the second example, we have a change in direction but not speed, which is a car going in circles, which was going to be very useful in circular motion and planetary orbits when we get to that later in the semester. And change in speed and direction can be given by a roller coaster. So physics relies on these Newton's three laws, and these Newton's three laws rely on this understanding of position and rates of change